Good morning, everyone. Today's lesson is going to be on finding light as a particle and a wave. The first thing we need to talk about is this thing called the wave particle duality. What that means is that light can act as both a particle and a wave in nature. So what this unit is going to do is it's going to bring together the first half of the year and the second half of the year. So in the second half of the year, we found out that light has some wave-like properties. It has frequency. It could diffract around barriers. It has wave interference, all which take upon wave-like phenomenon. But then we also know that light has a particle-like nature. What we mean by that is we could actually use lasers to etch and engrave things, or we could find out the velocity of those waves, or even light has a momentum, even though we kind of talk about it as a massless particle. Now, as far as quantum theory goes, quantum theory is basically talking about all the way back in chemistry, where we talked about an electron having a specific singular charge. You can't have half an electron's charge. You basically either have to have a charge of 1.6 times 10 to the minus 19 joules, or you don't. You basically have to have a multiple of that. So you can't have half an electron. And that's the same thing with the quantum theory. What this means is each individual jump, any kind of light packet, has to have a specific energy quality. So the fancy words quantum and quanta have been used throughout all advertisements. All it means is there's a specific amount of energy. Like if it says it takes 5 joules to jump from energy level 1 to energy level 2, then you can't jump to energy level 2 without the exact 5 joules. So that's all we're talking about quantum and quanta. So quanta would just be the plural of quantum. So if you took 5 joules to jump to level 1 and it took you 2 joules to jump to level 3, you could basically put those things together as how many quantum or quanta in plural. Next thing is actually talking about the photon. A photon is basically just a particle of light. So when you hear in those sci-fi channels, a photon torpedo, all that's really saying is it is a light torpedo instead of a metal shell shooting through space. Planck's formula. Now on page 5 of the reference table, you're going to now start to look at the modern physics formulas. The first one on there is E equals hf. What we could also do is expand this to E equals hc over lambda. We get this from doing the c, which is the speed of light, equals f lambda. We're going back to that waves unit. So if we reorganize things, we could basically substitute out the frequency and plug in c over lambda. So this would be h, which is Planck's constant, times the speed of light in a vacuum, divided by lambda, which would be the wavelength of that ray of light. So if we look at an energy of a photon, that's going to be our E, Planck's constant. This is on the front of your reference tables. If you look for the little h in the middle of the column, you'll find that it's 6.63 times 10 to the negative 34 joules seconds. This isn't a negative. This is just the hyphen thing we always use throughout the years, separating the columns. Frequency is still f, that's in hertz, or 1 over seconds. Speed of light in a vacuum is 3 times 10 to the 8 meters per second. Again, that's c. That's the speed of light in a vacuum. If we sent the speed of light through a different medium, that speed would change. And then wavelength is again in meters, and that's the lambda. The other thing is you could actually have Planck's constant in mega electron volts, but we're not going to deal with that in Regents physics. So for an example, if you had to determine the energy of a photon with a frequency of 6.59 times 10 to the 14 hertz, it's a really simple equation. Right now, again, we would go through the process. If we look at our knowns, we would have frequency. We are looking for energy. And then again, Planck's constant is a constant. So we would just use the simple equation, E equals hf. We would substitute all our values in, multiply it by the frequency, and then we get the energy of the photon. Needless to say, with another example, instead of giving us the frequency, what they're going to do is they're going to give us the wavelength. Again, all these equations could be reversed. They can give you the energy and ask for the wavelength. In this case, if they give you the wavelength and they ask for the energy, you're not going to use E equals hf. You're going to use E equals hc over lambda, because we know the speed of light is a constant, h is a constant, and lambda is what they give you with the wavelength. So if we substitute all those values in, we would get a value of 1.99 times 10 to the negative 19 joules. Hope you enjoyed. Be safe.